Hello, welcome to this video about set operations. So it's part of the old sequence, but in this video I'm going to do a short proof of one of the results that I used in previous videos. And we are talking about two sets in RD, A and B, which are subsets in RD. Okay. And I made a claim, and let's write it down. Claim, okay, that a convex hull of the Minkowski sum of A plus B is equal to the convex hull of A plus the convex hull of B, meaning that the convex hull and the Minkowski sum are exchangeable. Okay, it doesn't matter which you do first. So we want to prove this claim. Okay, and sometimes it's good to see a detailed proof, so to exercise and understand the concepts. So we have convex hull and we have the Minkowski sum, and let's see how we can get this inequality. So let's start from the first side, where x is some element of convex hull of A plus B. Okay, meaning that x can be expressed as a summation, from I to k, I equal to 1. Okay, let's make this 1. Okay, and here k elements, lambda I xi, such that lambda I sum to 1. Again, I goes from 1 to k, so it's a weight, and all the xi's, all of them are in the set convex hull A plus B. Okay, all of them, are in the set A plus B. Okay, so if this is the case, right, what we can do is to say now, let's take every xi, it's in A and B, so there exist, ai in A, bi in B, such that xi is equal to ai plus bi. Why? Because this is the definition of the Minkowski sum. Every point in the sum is coming from one point in A and one point in B, so every xi is like that. So let's rewrite x equal to the sum, I goes from 1 to k, of lambda I, ai plus bi, which of course can be broken into sum I goes from 1 to k, lambda I ai plus I goes from 1, this is 1 here, to k, of lambda I bi. And this is a point in conv A, and this is a point in conv B. So the summation is a point in conv A, Minkowski sum conv B. Great. So this set is included in the set on the right side. Now, if we look at the other direction, it's going to be a little bit more complicated in terms of the indices, but not that much. So if we take a point in this summation, so a point x, which is in conv A Minkowski sum conv B, okay, is x can be equal or can be expressed as two numbers, one coming from this set plus one coming from this set, so it's A plus B, okay, where A is in conv A and B is in conv B, okay, which will mean that A, okay, is equal to sum I goes from, let's say, 1 to n, okay, and let's call this alpha I AI, and each AI is coming from A, and B is equal to another sum, let's write it here, J goes from 1 to M, okay, and will be beta J Bj, okay. Now, if I take the sum, here it runs from 1 to n, here it runs from 1 to m. What do I do with that? I can look at a situation where I'm summing all the I and j, okay, where I goes from 1 to n and j will go from 1 to m. This is kind of a shortcut. It should be double summation. And I'm looking at AI, alpha I beta j, okay. And since the alpha I didn't write it here, but I'll talk about it. It's the alpha I should sum to 1, and each AI comes from A, and each Bj comes from B, and the beta sum to 1. So because of that, if I double sum this multiplication, it will also sum to 1. Okay. So now I can look at this summation, okay, which will be sum, again, going for I and j. The first one go to n, the second one go to m. I'll write it like that. And now I will write it alpha I times beta j, okay, this number, which is the multiplication of the alphas and betas, time the alpha ai, plus bi. And we can know that this is part of the A plus B. Okay, by definition, this is in A plus B. Okay, and this is going to be some linear combination of it, and therefore all of this, okay, all of this expression has to be in conv of A Minkowski sum B. Okay, so this set is included in the left one. So this concludes the proof, because the left one is included in the right one is included in the left one, meaning these two sets are the same. And that's why these operations are exchangeable. Okay, so this, as we say, concludes the proof. Okay, thank you for watching.